All right, well, thank you guys for coming on time. This is another item that will be on the final, so you can sell your notes to your friends or enemies who come late. But in any case, this topic of reassignment, I think, is very fundamental, and like always happens at a big university, I think it should be taught in our basic courses. But it's not, and I also think the basic courses jam way too much information into them. So I kind of have it both ways, right? Every professor has their favorite topics they want in the basic courses, and the basic courses just get totally overloaded for that. So I think this is the only place here that you'll hear about it, and it's a super, super useful technique. Before we get into the reassignment, the exam regrades, if you're going to get them, you got to put them up there, staple your regrade request to the front of your exam, not to the back. And yeah, I'm only accepting them for the next 10 minutes, so if you want it, don't be shy, go up there and put it up there. Okay, so time frequency reassignment, what is that? Well, we're doing spectral analysis, and we got long windows. We talked about long windows last time. We talked about noise-modulated sine waves and about doing bandpass filtered noise. So the bandpass filtered noise is from Stanford. It's the deterministic plus stochastic method, and then the noise-modulated sine waves was from here, from Kelly Fitz and myself. So the noise problems there are actually, in many ways, solved. They really work well. You can't solve all noise problems. There's lots of issues with noise. Like if you want something to sound breathier, you still have to sort of understand what does breathier mean, and you have to know how to manipulate. But at least you don't have thousands of components. Instead, you have tens or maybe 100 components to deal with. But there's another big issue, and that is this time smearing. When you take a long window, yeah, it's nice. You can analyze all sorts of different sounds, things that are non-harmonic or even polyphonic, that sort of thing. But one of the problems is it's like taking a blurry picture. You're just, each FFT has too much time in it. And so in music often, especially in the onset of sounds and in other kinds of transitions, you really want good time accuracy. Now in music it's interesting because unlike speech, in music you have very slow changing sounds normally, over seconds. Like a violin tone may last a few seconds, and yes, it changes timbre over those seconds, but very slowly. And if you were speaking during that time, you would have changed your mouth shape completely, several times per second. So in general, music goes slow, but when it doesn't, is super important. For instance, in the onset of sounds is one of the most obvious things to look at, is when a note starts up. In fact, when I was an undergrad here, I did this simple experiment. I had some additive synthesis stuff going based on the first paper you read, and then I did things where I took a trumpet attack and attached it, so the onset of the trumpet, just the first 30 milliseconds, and I attached it to violin tone, which was several seconds long. And it still sounded like a trumpet, just because the onset was a trumpet. Like the first 30 milliseconds determined what my ear thought it was. And then it sounded like a pretty crummy trumpet. Similarly, when I did it the other way around, it sounded like a cigar box violin, when I take a violin attack and stick it on a trumpet. But the attack is really what the sound. And then, it was an interesting experiment, a bit lo-fi, but it was really taught me the importance of onsets. So your ear is very sensitive to onsets in music, and in general, of course. So that's something to keep in mind. So you have this problem, and I see I copied this thing that was on the board in previous semesters onto your paper so you could look at it. But what I have there is you have a bunch of different windows, one at time T1, time at T2, and then I have one at time T50, T70, T82. It's just sort of a sketch. But in any case, you can see what's going on here. Here's a cello tone starting up. It has a more regular waveform, which I just I just drew something here. Don't take it too seriously in detail. But it has a pretty regular waveform after it starts up, but the nice grunty attack has all sorts of frequency information, all sorts of transient information in it that you want to keep. Now, if you do an MQ method on it, or any of the MQ methods other than this Loris that we developed, all of them have this problem. And I think it's one of the reasons it's going to be very hard to hear any long window sounds out of really good, because they all have this problem. I mean, it's a very fundamental thing. The reassignment is not hard to do, and I would strongly urge you, if you're going to do anything with long windows, do reassignment. In fact, I know of at least one person that went to work for Shure. This was years ago now, but and Shure makes not Shure. What am I saying? A meter company. Well, what are the little meters that we use everywhere here? What's that company called? Like voltmeters. What's that? Yeah, like voltmeters and different. Yet a different one. Anyway. Dang, my brain is, when you get older, it's in there. It's just my access time is longer than the lecture lasts. So maybe I'll think of it, maybe I won't. Fluke, that's what it is. There you go. See, I gave up, and then it comes up. Okay, so the Fluke meter company, one of the things they have is they have AC meters of various sorts, and I didn't even know the details, but they told me, oh yeah, they used reassignment, and it made a huge difference. It made their meters the best in the world. And why is that? Well, reassignment is a way to get time accuracy and frequency accuracy. Now, if you want better frequency accuracy, common wisdom tells you, oh, make your FFT longer. But there's a limit to that, right? If you want any sort of time accuracy, you can't just make your FFT longer and longer and longer. You're averaging too much stuff. You're blurring your image so much. So for whatever length of FFT you got, if you want better frequency accuracy, use time frequency reassignment. And you'll get, quote, for free, the time frequency trade-off. You're stumping the time frequency trade-off. You're actually getting better frequency for very little extra computation without doing a longer FFT. Now that sounds like magic and pulling data out of a hat. Well, okay, there is a thing here, there's a caveat. What you're assuming is that you're doing the FFT to try to find partials in music or sinusoidal components if you're a Fluke company. Right? You're trying to find frequencies present in there. And that's a really big restriction. An FFT will take any signal, whether there's repetitive stuff in there, there's frequencies present or not. It will take any signal. It could be random numbers. It could be random noise. It could be anything. You can FFT and then FFT again and get back the same samples. So, FFT is much more general than this, but in our work and in many, many uses of FFTs, what you're actually looking for is frequency components in the input. And if that's what you're doing, then you can do this reassignment. If you're looking for discrete frequency components in input, and when I say if that's what you're doing, another way of saying that is almost all the time, at least for all the applications I'm familiar with, people are actually looking for frequency components in there. So time frequency reassignment is a big, big deal. In this cello tone here, if you don't do time frequency reassignment, you got window T1 there, and it's to the left. It's before the sound even started, so it's silent. And then window T2 is still silent, but by T20 there, if you just do a normal long window analysis, right, you can see T20 is centered way before the sound even starts. But its right end here is already in the attack of the sound. So when you do this analysis with the MQ method or any method that doesn't use this reassignment, you end up getting a quiet version of the attack there already. So, if your window is, say, 100 milliseconds long, 100 milliseconds before, you already start hearing sound, and it comes in slower and slower and slower, and by the time you're here, you have it at half volume, where you actually want the attack, and then as you get, so you're totally smearing out the attack. I mean, to the point of really additive synthesis being a disappointment. And that's a serious problem. So, you don't want to do that. So instead, what you can do instead is use time frequency reassignment. So what is the idea with time frequency reassignment? You don't want the sound in synthesis to start way out here and not even get to full volume till way after the attack is over. That's crazy. It's a nice grunt cello attack. That's like a super important part of the sound. So If you're using long window method, the smearing out the text is a huge, huge mess. Here is a simplified example. Now, you'll see this window function that I'm using for the rest of this talk and in the paper you're reading is a simplified, the paper you're reading is actually not written by us, but in the work for audio, the windows actually look more like this almost always, especially at low frequencies. They kind of have a bump in the middle and then a pretty flat thing, and then, very long arms in time, but a bump in the middle. Here we're simplifying that. Here, this looks a lot like a raised cosine. In fact, it is. And that's okay. We're just simplifying the window here so that on the next page, the images make sense, so you can interpret them easier. But actually, this works with the Kaiser window or with whatever other window you might be using. So what's going on here? This is the reason to do time-frequency reassignment. Because if you don't, this waveform here, the dotted thing is just the window, but this waveform here, which happens at the very end of the window here, right, this is pulse, has identical, and literally identical, because we concocted this example, right? We calculated this example. This isn't a fake. Has identical magnitude spectrum as that. The MQ analysis, it doesn't, you don't get a distinction with long window methods between those two things. A normal FFT, if you just look at the magnitude spectrum to find your frequencies, and you don't do anything with, very smart with the phase spectrum, this and this look identical. And anybody looking at it can say, oh yeah, well that's pretty bad. In fact, if it's an audio thing, right, this sounds like a pulse and this doesn't. This sounds like a sustained thing. Now when you look at this magnitude spectrum here, this is all 0, right? And then you get this pulse. And this one here, you can see this frequency here. What's that frequency? Well, that corresponds to the frequency in that pulse. But you can also see it's wavering a bit. There's other frequencies in there, much lower frequencies. So there is low magnitude at other frequencies. And, probably something you wouldn't really notice and stuff, but actually if you interpret the FFT correctly, those low magnitudes at other frequencies, together with the phase information, is actually what makes it so that this pulse is way over here rather than the center. Right? You know that an FFT is invertible. You know that if you do an FFT and an FFT again, you get exactly that back. So if you do an FFT of this and do an FFT again, you'll get exactly this back. The problem is that when we do our long window analysis, we go into the magnitude spectrum, and then we start picking peaks in the magnitude. And that's okay, but you got to do more than that if you want to have a reasonable representation of the sound. Are we good? Any questions about this so far? So this thing, which has an event way at the end of the sound, has identical magnitude spectrum to that. Now, the Fourier transform gives you magnitude and phase. I mean, if you throw away half your data, well, duh, we get worse results. I mean, I don't know, what do you expect? All right. So, Fourier transform magnitude values are identical for A and B, but the phase values differ. Time frequency, so basically phase is encoding timing in some way. Time frequency reassignment uses this phase information very differently from MQ quadratic phase function synthesis, which you should understand, that's from the previous lecture, or short window method, which is from the one before the midterm. The short window method does use phase to correct frequency, and time frequency reassignment, besides doing time reassignment, also does frequency reassignment. So, it does use its phase information maybe in a smarter way than the quadratic phase function, but it's still very different from this. And, it's important to understand all those. In other words, it's important for the final. It's good to look at this now and again when the final rolls around. So what is time frequency reassignment? This is from your homework. And the idea of me talking about this isn't that you don't have to read the homework or that that you'll understand everything. What I want you to do is have an overview. Even the homework paper was just written for people in the field as an overview, an intro. Like, basically this paper is, why don't people do this more? And I read this paper, and I looked at it. There's a few little mistakes, by the way, in some of the graphs in the paper and stuff, but not graphs, in sort of a flowchart image. But the paper has these equations in it, and I want to talk about it a little bit just so you get the general idea. Now, as you know, in FFT, you have frequency bins as a result, right? Do we still use those words, frequency bins? Is that something people know from 310? Yeah, so basically your frequency and phase value is called a frequency bin. Why is it called a bin? Well, because it represents an area, and in the FFT itself, you're adding in values to each bin, just as the FFT is running along, doing its internal computation. So anyway, we call those frequency bins. Okay, so what happens here for time reassignment for every frequency bin? This is very important. Not just one overall, all the stuff in this window happens late. No, for each individual frequency bin, you get a reassignment for time, basically a correction for the time. Instead of saying, this frequency's center of gravity is in the middle of the window all the time, that's what you assume normally, but here you're actually getting a value for that. You're thinking, oh no, actually the center of gravity is to the right of the window. So for instance, time reassignment on the top example on the page would be way to the right. Would tell you, hey, it's on the right side of the window, so it'd be a positive number. The time reassignment might be negative, telling you it's way in the left of the window. Time reassignment for the second image at the top of the page would be 0. Why? Because it's pretty constant throughout the whole window. If it's totally constant, well, that means the center of gravity for it is in the center of the window. Everybody understand what I mean by center of gravity? Right? If you were to sorry to move this again, but if you were to put your finger underneath here and this time domain signal indicated, I don't know, something of weight, its magnitude indicated weight, then this one would fall to the right. If you put your finger here, these would balance. Okay. So, time reassignment. In this paper, it's important to understand the notation. And that's the main purpose of this page here. I'm trying to tell you what the notation is and what this stuff is, because if you don't think about this stuff, this is, for anybody who does time frequency transforms regularly, this is like the simplest thing there is, but when you're new to it, it's not, nothing is simple. So, what is that here? The T sub r is a time correction, and X just indicates that's the input sample stream. So you don't worry about that. That's just the whole data stream. And within that data stream, though, you're looking at a window centered at time t. And you're looking at a frequency bin that's centered at omega. Okay, so the t and omega, the t selects which FFT, which window of it are you even talking about. And the omega says which frequency bin are you going to be correcting. Are we good? So each frequency bin, remember, has a magnitude and a phase associated with it. Okay, so then we have this funny equation here. We have t plus the real part of stuff. Okay, now don't panic. The stuff will make some sense. There's actually details here that are more complicated to explain. But the first thing is, look, there's Fourier transform, there's short-time Fourier transforms that are inside that real thing there. They're complex numbers, right? I mean, you get complex results out of Fourier transform. So time, though, isn't complex. Time is a real number. So it shouldn't be surprising that there's an RE there, or maybe an IM, or maybe a magnitude. So there has to be something there that changes these complex numbers there to real numbers, right? So it sort of makes sense that that component, this RE, now why is it plus RE and not minus RE, or why is it not plus the magnitude of the stuff in those curly brackets, or why? Don't worry about that now. What I want you to do is, you can read these original papers about this. They're a little hard to read because they're generalized not just for Fourier transforms, they're generalized for all sorts of different transforms. And so it's hard to go to the original date. But you can do that if you want. In this class, what I want you to understand is much more important to me than if you can prove something about this math. You'll be happy to know I don't make you prove any derivations anymore. I did that 10 years ago and decided this is dumb. People don't even understand what they're doing, but they're going through the motions of all this math. And sometimes they get it right and sometimes they don't. But even the people that get it right aren't learning anything from it. So I'm not doing that anymore. What I want you to do now is actually understand what's going on here and believe that, yes, it's possible that this could actually work. You know, intuitively. Make sure that it makes some sense to you. So what's going on here? This is I over 2 pi, that's something. Here we got the frequency derivative, right, we get ddw here of this short time Fourier transform divided by this guy here. This is just a normal Fourier transform. Okay, so let's go to this last equation because it's almost the same as this, but this is the one we actually implement. And here it's reasonable to really try to figure out what's going on. This one here, this 1 over this here times that. So you got this with a complex divide, dividing that. Nobody likes complex divides. Okay, so the first thing is with these equations like, hey, how do you get from here to here when here you had 2 Fourier transforms and here you suddenly got 3? It's like, what's going on? All this is a trick to get rid of this complex divide, because nobody likes complex divides. They're a mess to implement. Okay, so what happens here, this is just an efficiency thing. This guy, STFTTH, okay, that's just this guy at the right. Instead of doing this derivative here, the way it's done there, it can be done by using a special window function. Just put that away in your brain. You know, that's just something to know. You don't have to prove it, but it's just something to know. These are efficiency tricks. Between these two steps, it's all efficiency tricks. So you've got this short-time Fourier transform within the function h, but you got that derivative thing in front of it, right? You can combine that together, and instead of doing that derivative thing, you can actually do that just by using a special window function. The math will end up being identical. We can go into that a little more. We can talk about it after class if you're interested, but just understand that for now. So the trick is, instead of doing this derivative all the time, you're just making a special window function FFT. Then here, the complex conjugate divided by the magnitude squared, that's just a trick to get rid of complex divides that you should have learned in some complex numbers class, or in 310, right? Instead of dividing by something complex, you can multiply by its complex conjugate and divide by its magnitude. That's all that is. No real magic there, okay? Now when you do that, you introduce a minus sign. But in any case, it's sort of believable that if this equation makes any sense, you could get to that one. And you don't have to prove that, but you can sort of see where the components come from. All right. So what are we left with here? This time reassignment, you do a Fourier transform with a weird window times divided by your original Fourier transform. Except instead of doing a complex divide, you got this thing. So that's basically how you do time frequency reassignment, and it requires an extra FFT. We'll look at that on the next page. But there's FFT number 1 is the one you normally do for a long window analysis anyway. FFT number 2 has a special window function, and I'll explain on the next page what TH is. Now, for frequency reassignment, you end up with the same thing down here, except it's yet a different window function. So you end up with a very similar looking equation, except it's plus imaginary instead of minus real, and you end up with a different window function. But that's all that's going on here, so the thing in the box is a really important thing. You do 3 FFTs instead of just 1, centered at each T. Now, FFT is one of the most efficient computations around. Right? It's super optimized. There's always good libraries for it. So this is really good news. This is not very much extra computation. To do 3 times the computation, you get way more accuracy. Just compare that to using a longer window or something. If you wanted to get accuracy that way, A, your thing would be really smeared and wouldn't be very good data, and B, it would take even more computation. So this is a win-win thing. All right. So down here, this is the paper. Actually, you're reading it, so you will get familiar with that. It's in your homework assignment. So yeah, the final equations used there don't have a complex divide with this division trick that you should know. If you don't, look it up or ask a friend who's better at math. The traditional method, again, 1 FFT is done. And the way we would call it here is STFT, short time Fourier transform, sub H. With X as the window thing, and then the T and omegas are just choosing which window, X is the input samples, T is choosing which window, omega is choosing which bin. But you would have to compute those short-time Fourier transforms for each window. Now you're going to do 3 of them. Same data, but different window functions. Questions about that? All right. So, here are the 3 windows. And I want you to intuitively understand these windows. Now again, we actually use a Kaiser window with a shape function. Actually what we do is say, well, how many dB side lobe rejection do you want, and the main lobe width. But in any case, you end up with a more complicated looking window function. Normally it has longer legs on either side, but that's okay. This is just a raised cosine. We're keeping it simple here. So we've got 3 FFTs here. Now they're on the same data. You have one windowed thing. One windowed thing, and the top window function is one you normally use on it. But you do another FFT doing this window function, and a third FFT using that window function. Now be really careful. A quick look at this window function. People say, oh, it's just a sinusoid. No. if you put a sine in there, it's not going to work. Details matter in this stuff, right? I'll explain what it is, but it ain't a sine. So the top one is let's say that's the window function you're using. It's a raised cosine window in this case, but that's the window function you're using. It's used for computing the spectral magnitudes, and it's using for normalized. What do I mean by using for normalized? Look at the previous page. In the denominator, right, the thing you're dividing by is also your normal FFT. So it's using for normalized. What does that mean? Well, you have to be careful. Like if say all of your values are really small in your FFT because the sound is really quiet. Well, you don't want to have that result in, oh, then every time frequency reassignment is really small, like frequencies reassign only a tiny bit, just because your signal is small. So you need to normalize for however strong your signal is. And that's what that normalization is. That's what that divide is about. Does that make sense? All right. So top FFT, that's the normal FFT you do. If you were doing MQ, that'd be the only FFT you do using that window. But if you want to do time frequency reassignment, then you do the second window. You can get an intuitive hand-waving understanding of this window. And I want you to do that. Now this window is drawn, I think, labeled wrong in the paper somewhere or something. But anyway, what happens here, at the center of the window, we call this 0, right? It's going through 0. And then you see it going down here and up here. What this really is that top window times a ramp that goes from -1 to 1. That's all that is. Right? The ramp goes through 0 at the center. So this thing goes through 0 at the center. On the negative side, well, the ramp is negative, so this thing, that ramp multiplied by that gets you this negative bump, and the positive bump is just the positive side. So all this is really, it's as if you took your normal window function and all the samples of that window, you multiplied them before you did the FFT, you multiplied them all by a ramp from -1 to 1. And then you did your FFT with the window. Now, instead of multiplying by -1 to 1 as a separate thing from doing an FFT, you just combine the two. If you use a window function, that's like that, because after all, the window function just gets multiplied by the thing. So if that's your window function, that's your ramp from -1 to 1, then this is how your window function would look. Can people see that thing is just a -1 to 1 ramp times window function there? Okay, good. If you see that, then, well, why the heck are you multiplying by -1 to 1? Okay, this is going to be used for time reassignments. In fact, the T just indicates you multiplied the window function by a time. Well, -1 to 1 is time through the window. But you're multiplying the window function -1 to 1. So, how do you intuitively think about this? Well, say you have samples that only exist on the left side of the window. This multiplies them by negative values. Right? Because they're over here where it's negative. Say you only have samples like your bump, like on the first page, or first example, stuff only happened on the right side of the window. Well, that gets multiplied by positive values. let's say you have stuff that happens all through the window, like the second example. Well, the left side gets multiplied by negative values, the positive side gets multiplied by positive values, and when you add it all up, you're going to get no reassignment out of it. The center of gravity is in the center. So all this is weighting the early samples negatively, the later samples positively. Does that make good sense? Now you got to normalize it because, samples just on their own can be negative or positive anyway, and there's all these other issues, plus the signal may be big or small, so you have to normalize. You have to do the divide by the first FFT still. And that just, so everything is normalized properly. But here, the idea of this thing is you're multiplying samples that happened early in the window, negative, ones that are late, positive. So if you go back and look at your time reassignment equation, you can tell when it happened early and when it happened late. All right? So you're going to use the normal FFT that you do up there to find your magnitudes. That doesn't change. You're going to use those for finding magnitudes, but now you want to figure out a better frequency and a better time. So for every magnitude value you get out of your FFT, out of each FFT, you're going out of each window, you're going to improve its frequency and its timing. So the time reassignment for that bin will say, hey, did this frequency, whatever this magnitude is, did it occur on the left side of the window and not later? Is the center of gravity in the left, is it in the right, or is it all the time in the center? Is it uniform? Okay, how many people can grok that? Can I see a show of hands of people that got anything out of this so far? Okay, well, good. You're going to read this anyway, so you can read the paper and it'll help some. I believe the mistake in the paper, though, is drawing this window function wrong, which doesn't help if you're just trying to understand it. The paper's good, but it had a dumb mistake in it that, for some reason, the editors didn't notice. Yeah?
I'm curious as to why, so basically the middle one is a multiplication on the top one by that ramp from negative 1 to 1, but the scale goes from like 0 to 1 to like negative 40 to 40.
Oh, yuck. Uh-oh. Now I'm going to have to come up with something. Why did I... That's a horrible scale. See, yeah, these are real values. Now, if I had drawn this is taken from real program, real data. And the problem is always, it has real things in it. If I had drawn it now, I would have just written -1 to 1 here and -1 to 1 there. And you have to normalize it, depending on the length of your window, right? This is because your window is 500 long, the -250 and 250. -40 to 40, I don't know. It's a scale factor. I wish it were divisible by 2 pi or something. Then I could say, that's just, this. I don't remember. I'd have to look at it again. Good question. I've been showing this now for, nearly 20 years, and you're the first person to ask that. You got me stumped. Anyway, it's got to be a normalization factor because, in the end, you want the time reassignment. What units do you want for it? Do you want sample units? Do you want millisecond units? Do you want, it's going to be, and I don't even know what this was for. It's going to be for one of those, so that the value ends up being samples or milliseconds or what. But I don't remember. It's also not exactly 40, right? It's just a little bit. Actually, I think it was a little bit higher than that. Maybe, I don't know. In any case, it's probably, it's probably something really easy that I can't answer. I can look it up and try to figure it out, but I don't know if I'll be able to. This was a long time ago. If anybody, I can look up the paper and see what it says. I hope we wrote it, we, meaning Kelly Fitz, remembered to put it in the paper. If it's in the paper, then that's good. Then I'll be able to tell you. All right. Yes. So now, FFT number 3, if FFT number 2 made any sort of intuitive sense to you, that's great, because I'm going to hand wave away FFT number 3. What is this weirdo function here? This is the derivative of that. Okay? That's really all this is. And this is where hand waving comes in. Why would frequency reassignment have a derivative of the window where time reassignment has a ramp? Well, actually, if you look at your FFT, if you look at your time frequency, what do they call them, pairs? Correspondences? Like, like in time domain, a multiply is a convolution frequency domain, things like that.
Properties.
What's that?
Like the properties table?
Yeah, that funny properties thing where you have, what corresponds to what? Well, if you look up a ramp, it corresponds to derivative in frequency. And, well, this is a time thing, right, time reassignment, this is frequency reassignment. So that's my best lame attempt to have you, well, you could believe it's true. Because in the properties table, right, just, this is trying to do the same thing, this is trying to do the same thing as that, except this is in the frequency direction, this is in the time direction. But they're basically doing the same thing. So one is reassigning frequency, one's reassigning phase, time. That's what this here is, a frequency domain dual. Oh, okay, we used to call them duals, but maybe dueling isn't a thing anymore. That's old. Anyway, so time domain dual, or the time domain properties tells you that if you have the time, if you have a function that's a ramp, that corresponds to a frequency domain derivative. And that's my best hand-waving thing. If you could understand the time reassignment and believe that, that's really good. I won't ask you too much about the frequency reassignment. I just want this to be believable. It's not, we have half a lecture to spend on a topic that could be a class, and I just want it to be believable to you. Okay? So that's a hand-waving explanation here for the third window. Now, if you go back again, just to touch basics again, what are you going to do? Well, normally you would have a long window function that might look like that. Certainly a Kaiser window could look like that if you put the right parameters in. You usually use a different shaped Kaiser window. But in any case, if that's your window, then at each FFT you would also do one with this shaped window, which is easy to generate once before you even start. It's very efficient. You make an extra window table, which is that window function multiplied by ramp minus 1 to 1. And then you make a third table, which is whatever window you're using, the derivative of it. And that's it. Then at every window, every window thing, you go over hop size. Instead of doing one FFT with that top window, you do 3 FFTs, top window, middle window, bottom window. The top window gets you your magnitudes. The middle window is in that equation together with the top window results, top window just being used to normalize it. But the middle window gets you time reassignments for every magnitude you've got. And the bottom one gets your frequency reassignment for every magnitude you got. All right? Very cool. Okay, so that's enough of that. You're going to read a paper on it. Hopefully something will stick. Even if you don't remember this 10 years from now when in your work on totally unrelated stuff, who knows what you're actually doing, monitoring some microbiology process or building spaceships that go to Mars or whatever you're doing. This will come up sometime in your life, and you'll sort of remember it and say, oh yeah, there was that weird trick if we want better frequency and time accuracy. So remember that. In my work, Fourier transforms, long windows, are basically useless without this. You can't make high-quality audio, as far as I can tell, without this. Now, some would disagree because there are, certainly lots of other algorithms, but it just seems like you add this to any of those algorithms out there and it'll improve them. Okay, now I do want to talk about algorithms out there because earlier I talked about the Smith interpolation, this parabolic interpolation from lecture 14. What happens here is, in this thing here, using time frequency reassignment, right, you have that little thing, is that in your, did I put that in your handout? I did not. I should include that. But this little thing here is, you can tell if you did parabolic interpolation, it would end up to the left of the center peak there. Time frequency reassignment also ends up to the left, but every one of these magnitudes, all the neighboring ones, they all try to reassign to the same place. So it's kind of cute. And yeah, so it's actually a quick way to tell too, like how much of this stuff that's spread out there is actually due to one sinusoid. Because in your FFT, you also have this spread of things, and you can pick a peak. Anyway, you can do your peak improvement. Now, you don't have to look at 3 of them and do an interpolation stuff. Instead, you just use the peak one, and you see how it reassigns. Because if you look at its FFT, if you look at your equations, you've used the phase information, well, and magnitude information of every data point in the whole FFT to get the best possible reassignment in frequency. Okay, and that's why this is better, like, than the Smith interpolation, because parabolic interpolation only takes 3 points in magnitude. So it takes half the data from 3 points, and only the magnitude data from 3 points, and improves frequency that way. This thing takes all the magnitude and all the phase data globally from the whole FFT, and it gives you the best possible interpolation you could get from the data. So it's less noisy. Now, I have to say here, because, you know, the Smith interpolation is from Stanford, and this other stuff is stuff, as far as I know, has only been done here and by people that use our software, the Lemur open source software, Aloris rather, open source software. But in practice, most of the time, the Smith interpolation is good enough. Most of the time, the amount of noise you get there and stuff is just not very significant. This, you know, compared to just doing the vanilla MQ, the Smith interpolation solves your problem. So the simple thing does work. Now, in defense of time-frequency reassignment, well, why not do time-frequency? You already did an FFT. You know you got an FFT subroutine. Just do it the fancier way. But in practice, I looked around, or Kelly Fitz and I looked around for examples where the time-frequency reassignment, the time reassignment, works substantially better because it's using global data. It's, you know, less noise, blah 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 blah. And the only places where we could clearly see a big difference that commonly came up was at very low frequencies. If you're at a very low frequency, it's better to use global data. And what happens is your peaks are close together at very low frequencies in your spectrum, and it just turns out when you're looking at these neighboring magnitudes, you know, they're being affected by the next peak over and stuff too. If you use global data, you get a little bit, you know, you get another octave at the bottom. So that's worth something. But in general, if you really just are interested in magnitude information and frequency information, the Smith interpolation works. So this is, quote, better, but mostly in a mathematical sense, and there's only a few situations. Yeah, that gets your frequency reassignment. Now, the Smith interpolation does nothing for time reassignment. So the smearing out of data, which is a fundamental problem, is not solved by that. And so I very much encourage you to do time frequency reassignment anyway. If we want to compare long window methods here, we've got this fun image here. First thing I want to say about these images, because I've showed these same images now for 20 years, and unlike the question about what was that axis, people have asked about this. First thing first, this is just a bottom left corner of data you would have. Your time, actually, you have many time windows up to T sub big M. And you have many frequencies all the way up to omega big N. Right, and I'm only showing 8 frequencies. No, in a long window, you get a lot more than 8 frequencies out. Right, you get hundreds and hundreds of frequencies out. You get probably hundreds of windows out. So this is just showing a little corner. And all this grid is really doing is showing you where does it keep data. It's not showing you very much about the data. So what is this? This one here is representing the short-time Fourier transform, just keeping all your data, which some people call phase vocoder. Phase vocoder is an unfortunate word because it's used for lots of different things. But sometimes you'll see phase vocoder synthesis, and this is what they're talking about. Sometimes. So what happens, this is the window that you had at T1. You did an FFT there, just a normal FFT, a signal window function, you know, with your favorite Kaiser window, and you kept all the data at every frequency bin. Then you moved on to your window. You moved over usually 3 milliseconds or so, much overlapping one, and then you kept all the data. And then you moved on to the next window, you kept all the data. So you keep all your data there. So that's a phase vocoder. And the nice enticing thing about that is, well, you don't throw away any data. You don't look for peaks in your thing. The disadvantage of doing that is that, well, you have a lot of data. And just looking at the data makes it sort of hard to interpret many things about it. Certainly makes it hard to manipulate. And some people claim to have great results, Yeah, but it's a difficult thing to do a lot with it. But people do work with that. That's a real thing. So that's a phase vocoder. Then there's MQ. It's like this, except in each window you picked only the peaks out. Now you will have a lot more than 3 peaks. Again, this goes up to a lot more frequency values. Just sort of showing the bottom left corner of, this is an actual analysis data. So it is what it is here. But here what you're seeing is here's a partial that goes, we connected them across. So those are the bottom 3 partials is all you're seeing, the very beginning of them. All right? So this is the MQ analysis. Still, any data that was collected centered at T1 is considered T1. And, unless you do the Smith interpolation, but the vanilla MQ analysis, if you don't do the Smith interpolation, also keeps the frequency at whatever the bin frequency is. So the time is stuck, the frequency is stuck. Time is stuck frequency. So you're just picking data points out of this in MQ, but you're not doing anything else. Then you're going to do that quadratic phase interpolation thing. So, yeah. So that's what this is. Now, if you do time frequency reassignment, it looks like this. Okay, again, this is a small excerpt taken from an actual analysis. But this data point here, these windows are long. They're very much overlapping windows. Remember, your windows are easily 100 milliseconds long, and you have a hop size of 3 milliseconds. So in time frequency reassignment, this guy here says, hey, I'm reassigned over here. This guy, and the frequency reassignment says I'm reassigned up. Here, this time reassignment says I'm over here, and the frequency reassignment also puts him positive. Anyway, you can see they all just reassign like that. So this is a much better representation because it tells you, for instance, at the beginning of a cello tone, hey, this happens much later. It's not happening right away. Now, what we did here, what is not shown, actually you get reassignment from way far over because there's so much overlap in windows. And if the reassignment is too great, we just throw away the data. Because, look, if you have largely overlapping windows, you're going to see the same data point again in the next window, and the window after that, and window after that anyway, right? And the windows are really, really long. So if there's a huge reassignment value, just chuck it. It's actually a way to, it's sort of a confidence thing, too. You can tell, hey, this data isn't good from looking at that. But anyway, so here's reassignment to over here. Now, what you'll notice right away is this is not on a grid. People like grids. Why do people like grids? Because MATLAB is super useful. MATLAB is not real great at linked lists, right? So one of the things that sort of hurts this kind of analysis is MATLAB is incredibly useful as a tool. In fact, so useful that if the tool doesn't work for something, then often it's just not done. So MATLAB does have some time frequency reassignment stuff, but it keeps it on a grid and stuff. It doesn't do the, it just doesn't deal with sparse matrices and linked lists that well. So anyway, so this is a problem for people that want to manipulate this data using standard engineering techniques, is that, hey, this data is unequally spaced. MATLAB likes arrays. It likes matrices. Right? And if you wanted to represent this in MATLAB, you could, but it would be a lot of work to try to do anything with it. Are we good? So that's one reason why it doesn't have much. There is this open source LORIS, which is mentioned somewhere on here, somewhere in your homework, that if you wanted to mess with this, you could. And there's also some websites that'll graph the stuff for you, get you some help. There's also a Python interface if you're into that. But anyway, does this reassignment make sense? So, what can I say down here? Short-time Fourier transfer, yes, you retain everything. MQ retains its selected time and frequency points, and reassigned is distributed continuously in time and frequency. One thing that's interesting here, notice how the time reassignment goes to the grid. Now this particular sound isn't the really low, I forget what this was from, but this isn't the low cello tone. It wouldn't happen that fast there, but look at this. Like here, this guy reassigns way over here, this over here. Well, this is the onset portion. But look at the time once you get into the sustain. It's actually sort of staying on the time grid. That's because it's sustained, right? The center of gravity of the data is throughout the window. So you can kind of see that even in that tiny little excerpt. What else can I say? Oh yes, exercise here. Draw this, but include Smith's interpolation. How would the Smith interpolation change this graph? Right here we have these arrows that reassign time way over here and frequency way over here. Well, what would happen over here? You actually could do that because you have the frequency reassignment here. Although the Smith interpolation, it doesn't do time reassignment, right? It just gets you better frequency. But as I said before, it usually matches pretty well. So all you do is you look at this point here, and you say, oh, it moved up this far. Well, that's about what the Smith interpolation would give you too here. But it would stay on this x-axis point. This one here would move up to there, so the vertical would be the same, or close enough to the same, unless there's something very special about this. The Smith interpolation, like I said, is less fancy, but mathematically, but it works for most things. I mean, you can find problem cases, but most of the time it's about the same. So you could draw that. I guess now that I said that, I can't put that exact thing on the final. Or maybe I can, I don't know. But anyway, I have to ask you something on the final. Do understand these pictures, do understand what this stuff means. This is an especially important topic for me because I know the majority of you are interested in music for some reason, but are not going to do it as your job. So the things that you learn in here, other than just getting more familiar with listening to what low-pass filters and such sound like in the lab, and another really useful thing is this time-frequency reassignment. All right, so here's on the third page. This doesn't project real well, but this is reassigned bandwidth enhanced cello data from real cello tone. So this is 0 to 781 and 0 to 0.143. So this is a graph that shows you the cello analysis. Unfortunately, this projector doesn't do it so well, but it's only showing the first 0.143 seconds, and it's only going up to 781 kilohertz. The half sample rate is around 20-some kilohertz. So it's showing the lower frequencies of the beginning of a sound. Now, on your paper, maybe it's a little better. The blue color means it's noisy. That means that it found a peak there, but the data is pretty spread out. And so, again, from last lecture, you know that what we do there is multiply by, spread out the bandwidth of all the blue guys. Then a black color is more sinusoidal, more narrow band, a real partial that you can really tell. And then just darker blue or lighter blue or darker black, gray, I guess, or lighter. I'm sorry. The gray scale or the blue scale tells you just how loud it is. What the magnitude is. So this is the beginning of that sound, and it's the data doesn't look the same as MQ data would. It isn't on a clear rectangular grid. It does eventually get there, but it takes it the better part of a second to get there, to be on a much more rectangular grid. So that's kind of cool. Questions about that? Beware when you do cello stuff. I mean, this one goes up to 781 hertz, but there's data much higher than that. So this is just so you can look at it, because otherwise this would be squished in the bottom 3% of an image. Yeah. All right. I am done with that topic unless there's questions about time frequency reassignment. We've got a new major topic, so you're ready to clear your brain. I'm going to hand out a ear. I'm going to pass around the ear that you saw up here. This ear is approximately to scale. You'll see the outer ear here with the pinna and the outer ear canal, then the middle ear here with the hammer, anvil, and stirrup, the three little bones. And the inside of the ear here, the inner ear with the cochlea there. So in the inner ear, right, the cochlea is filled with liquid. The outer ear is filled with air. And for all you engineers, right, these three little bones here are impedance matchers. They basically, you have to go from air vibrations to liquid vibrations. And they are an analog, well, biological hack to do that. And work pretty well until you get my age. There you go. So it's just something to look at. It's kind of funny, the blue snail thing there is the cochlea. It's all rolled up. Sort of interesting that it's rolled up rather than straight. Here, just to make it simpler, we make it look straight. But actually, it turns out if you unrolled that snail thing, it would go too far into your head. It would not be good. So you don't unroll your cochlea. Okay, so this is a picture of the same thing that I'm handing around. Again, Pinna is the outer. Here's the external canal. This is the middle ear here, and this is the snail thing. Now, the snail thing has these cool semicircular canals up there. Those are for balance. We're not going to talk about those much. We're going to talk about the rest of this rolled up guy here, the cochlea. So, let's talk. We're going to talk a little bit. Again, this is another topic for a semester course, or maybe even for a degree program. So we're going to kind of fly through very basic. Has anybody ever looked at the basics of psychoacoustics and what the ear is? Anybody here? Okay, so it's not a waste of your time. It's very simple things. I'm going to talk about lots of different topics here, but just so you have an idea of what goes on. So in psychoacoustics, of course, we care about how people hear things. It's different than what engineers normally do. Engineers say, oh, are these two the same? And it's always the least squares difference or something simple like that. Here, when we say, are these two things the same, for example, that means do they sound the same to a person? And that's a very different question than the normal engineering question. So, technical terms here. Horizontal localization. We got binaural localization. So what does that mean? That means horizontal localization means in the plane of your eyes and your ears. It turns out your horizontal localization, meaning telling where did the sound come from, is quite accurate, at least compared to any other localization. So you can hear quite accurately on this axis where did it come from. In fact, to the point where if you hear a noise that comes from above, you only know approximately where it is, but the first thing you do is you look up there, because you also want to get visual feedback. And then all of a sudden, when you're looking at it, hey, it's on your more accurate axis of localization for your hearing system too. So by moving your head up and looking, that's a good thing. So what are your main binaural localization cues? Well, one is amplitude. If the sound is coming from over there, guess what? It's louder in this ear than that ear. And I like to scuba dive, and that's one of the things there is, right, when you're underwater, that doesn't work so good because water isn't very compressible, so the amplitude doesn't drop off noticeably. The speed of sound is way too fast. There's lots and lots of problems underwater. So it's really hard to tell where things are coming from underwater. You're always like looking all around trying to figure out who made that noise, or where's the boat, or whatever the sound is. That's amplitude. Another thing is onset time, especially for higher frequencies. If there's a click happening over there, now clicks and snaps and stuff, for survival are pretty important. You want to know when the mountain lion is sneaking up on you, and the mountain lion's pretty quiet. So, or whatever it is, or a snake slithering. So when you hear a little snap or click, you're pretty good at hearing that, and that has a very fast onset. So you can tell, your hearing system can tell where it is just by when does it reach this ear versus when does it reach that ear. So that's a really important localization cue. And then for lower frequencies, the phase is important. When you get wavelengths that are way longer than your head, you're depending on where the sound is coming from, you have different phase in your right and left ear. So for longer wavelengths or for lower frequencies, phase difference between the ears can be very important. So you use different kinds of cues for horizontal localization, but the onset time can be extremely accurate. The phase localization I know not as much about, but yeah. Questions about that? All right, so that's horizontal localization. Now vertical localization, what is that about? Well, one thing you can look at, it's hard to study this because your vertical localization isn't very good. So that's one problem. And, but one thing that you can really find, and that also if you simulate it really works, is you have two main paths in your ear. Let's try, and this for lower frequencies off of your shoulder is really important. For higher frequencies, bouncing off your pinna is important, the secondary pass. But let's talk about the shoulder. So you have your shoulder. So if you have a sound that's up there, the two primary paths in your ear are going to be direct into your ear, right, the direct path, and then a slightly longer path, which bounces off your shoulder and then goes in your ear. Both of those go into your ear. They just get added up there, right? They just go into your ear. But we get a comb filter effect due to that because there's two paths into the ear. What are we looking at there? Look at that top graph I've drawn there. It's a little excessive because actually the reflection off your shoulder is far from perfect. So it turns out that the shoulder reflection is much more dispersed and not as loud and not as good as the main. But if you had exactly two signals by time with some constant delay on one compared to the other, you would get a comb effect like that in frequency. Why is that? Why does it go to zeros? Well, when that difference in the path length corresponds to 180 degrees of phase, right? At some frequencies, that's going to be exactly 180 degrees of phase. And at those frequencies, you get those dips. Well, 180 or 360 plus n times 180, I should say. But whenever you get to frequencies where it just totally cancels out, you get that comb filter effect. Does that make sense? So that's what these equations are about. You've got this frequency thing here, but now you've got two different paths, right? So 340 meters per second divided by the wavelength, but now you've got two different paths. And you have this equation here, and with that you could draw it. Y is minus 1/2, again, because you've got to be 180 degrees out of phase. So this is based on the delta path, and it's just derived from the first equation. But I want you to intuitively understand it. Hey, anything that's 180 degrees out of phase is going to get you a minimum point, not a zero if the two signals aren't identical. Up there I drew saying for, but, and this equation tells you where those minimum points are. So if your hearing system can detect those minimum points, then you do good. People argue about, is it actually mostly done in time domain or frequency domain, this process, or some combination? I assume it's actually some combination. You certainly aren't going to get a perfect comb like that because the reflections aren't perfect. And depending on what clothes you're wearing and all sorts of other things, your shoulder reflections are different. So there are a bunch of filters you can get. They're called head-related transform function. What is that? What that is somebody took a dummy head, something shaped like a human's head, and put microphones inside the ears. And generically, it's like a human's head enough. It's got shoulders on it even. It's got hair. It's got some other features. And then they recorded sounds coming from clicks. Impulses, basically, coming from all different directions, the horizontal, in different angles, all that kind of stuff. So now you got this whole family of filter functions or impulse responses for different angles, horizontally and vertically. And that's what a head-related transfer function is that set of filters. You pick one out depending on where you want the sound to come from, you run it through it, and then if you're wearing earbuds, it's amazingly good. Just, as a 385 project, if you, I don't know, maybe it's not appropriate, who knows, but for whatever thing, sometime in your life, you can find these head-related transfer functions online, or sometimes they're in the form of impulse responses in time domain. It's the same thing, right? So they're convolutions that you do. These convolutions are pretty short. You're usually talking about like maybe 128 samples, maybe a little bit longer, but they're not super long. So they're not hard to compute on any computer or any microprocessor, or on your FPGA. But you can do a head-related impulse response or head-related transfer function, same thing, one's time domain, one's frequency domain, and make things sound like they come from different places. And with earbuds, it works great. Now, if you're developing your own software, don't wear earbuds right at the beginning. You don't want to blow your ears out. But eventually, headphones and earbuds are great. If you do it through speakers, it only sort of works, right? Because you're a different distance away from the speaker. If you're too close to the speaker, you got near-field effects. If you're far away from the speaker, you got all sorts of delays and other stuff. Really, this is a place where things have gotten a lot better since people have been willing to wear headphones or earbuds. All right, questions about that? That's localization. That's a good class that you can take in some other department. We just finished it in a few minutes. So yes, it's a fast thing, but it's something to know. If you're working on video games or something, the fancier video games use head-related impulse responses. Unfortunately, that's considered fancy, where that's like step 0. What you really want to do is do specular reflections of sound off the walls of your game scene, but audio is in its infancy for games, so that doesn't, you don't see that yet, or except in very experimental situations. You only see that for video, right? For video, we got GPUs. They do all that stuff. Okay, so now we got another thing. Primary resonance of the ear. This is also an outer ear thing. The primary resonance of the ear is around 2.5 kilohertz. You know that from your equal loudness curves. Remember there was that dip at 2.5 kilohertz? Or around 2.5 kilohertz. So that's a resonance of the ear. That has to do with how long is this canal here. And did that ear make it all the way to the back yet? Yeah, here. What's kind of funny is that the resonance is for a wavelength that's 13.5 centimeters, which even if you're not very metric is a lot longer than that. Why does this resonate at 13.5 centimeters? Well, if you remember from your high school physics, this is approximately an open pipe, right? It's a quarter wavelength resonator. And it's approximately a quarter of that length. And that's why that's the resonance. So that's a really important number, because in speech formants and all sorts of things, that area, in all sorts of hearing, that area is especially sensitive. We'll talk about later in this class the creaminess and those kinds of sound features. They all are in this range. There's lots of different things that happen in that range. You're especially sensitive there. So yes, so where did I go here? Yes, so the wavelength that's resonating there is 13.6 centimeters, but your outer ear canal length is a quarter of that long, and because it's like an open tube. Is it exactly an open tube? Of course not. It's bent. It's got earwax in it. Well, this one doesn't, unfortunately, but a real one has all sorts of other things. Approximately enough, it turns out your resonance is still there. Okay, so now at the end of the outer ear there is the eardrum. And then going into the inner ear is the oval window. Between the two, if you saw this here, are the 3 smallest bones of your body, actually 3 of the 6 smallest bones of your body, because you got one in each, one set in each ear. But those are the hammer, anvil, and stirrup. And they go from air vibrations to liquid vibrations. No small feat. Again, I like to scuba dive, and it's funny, people above water can scream their brains out, and to actually hear that underwater is basically impossible. Not just because of the bubbling and stuff, even if you're not breathing at the time. There's just very little transfer. You need some sort of mechanism for transferring into water or into any liquid out of air. So that's what hammer, anvil, and stirrup do. You still don't get a huge vibration in there. The energy in the air is very low, right? So the watts, or whatever you want to call it, is quite low. But still, with this impedance matcher, you do reasonably well. So its function is to take these air vibrations that are vibrating the eardrum and get to the oval window of the inner ear. So in the middle ear is this impedance matcher. We call it hammer, anvil, and stirrup. Why? Because the bones are sort of shaped that way. There's cool Latin names for it too, but these are easy to remember. And if you look at the bone, you can tell which one it is. One thing to mention, there's in speech and hearing, hearing loss and that sort of thing is a huge topic. So again, I'm just in passing mentioning this. Right, you get osteoporosis when you're old. You have trouble with your joints, with your bones. And, well, hearing loss, why do you get, that's the main cause of hearing loss for older people. Why? Because this impedance matcher is made of bones. And they get old and creaky and they don't do their job very well anymore. So it's the same sort of thing that makes it hard to walk and makes lots of other things hard. So that's a big cause of hearing loss in the middle ear there. Okay. So now we're going to do the inner ear. Again, we're going to draw a picture that looks like this, which is sort of a joke. But here's the bone chain, or the hammer, anvil, and stirrup. Here's the eardrum on the outside. This is that snail thing, ignoring the semicircular canals, sort of straightened out, just unrolled. Not because it would be functional anymore if you actually did that to anybody's cochlea, but just to look at it. So what happens here? The highest frequencies here, so you got this oval window here. It's going to vibrate the liquid. It's vibrating along here. Vibrations can pass through there. All the way to over here, there's a round window at the end that tends to damp vibrations a bit, so they don't reflect forever. But so you've got this. You've got the cochlea here, and down the center you got the basilar membrane. It's about 35 millimeters long. It's got about 30,000 receptor cells. I say receptor cells, these are all specialized hair cells, because there's also active cells there that try to amplify the vibrations, because the vibrations are really small. So your ear isn't just a passive recording device. It actually tries to amplify the vibrations. The receptor cells, though, take the local vibrations and provide them to the oral nerves. Yeah. So you've got complicated things going on here because you've got fluid vibrations, which are, at first initiated by the oval window vibrating due to the three bones there. But you also, the membrane itself isn't totally stiff. It varies in stiffness. It's not even totally flat either. It's just a complicated setup. So the membrane isn't stiff, so it vibrates also, and it's got active hair cells on it trying to increase vibrations. So it's a complicated setup. There is a place principle, which is kind of cool. And this is what, at first when engineers figured this out, they said, oh, it's doing an FFT, how cool. Or Fourier transform. Well, it's not quite that, but a little bit like that. There's a place principle. So the lowest frequencies are picked up here. And the oscillations are the lower frequency component oscillations are greatest in this part. High frequency oscillations are greatest in this part and picked up there. So it does have this place principle. It does, along the cochlea, you get different amounts of vibration depending on your frequency. So it does sort of break things down into frequency components, sort of. You got to be really careful. That's about where it ends. It's not as Fourier transform. For one thing, a Fourier transform isn't active. A Fourier transform's got nothing in it that's got some circuitry to try to amplify your signal or something. So it's not like that. So you've got high frequencies here, low frequencies there, and that's called the place principle. That the frequencies are distributed along the ear. It's only about 35 millimeter long. That doesn't vary very much by person. Obviously, it varies a little bit. And there's about 30,000 receptor cells. And again, you can calculate the number of receptor cells per millimeter. You can calculate all sorts of great things. But those oscillations are very important. Now, autoacoustic emissions, what is that about? That's something that happens sort of when the system misfires. Like, say, for instance, you play a click into the ear. Your hair cells in there, the ones that are trying to amplify, see this click, oh, good, the sound's coming in. They try to amplify that. But then it's just a click, it goes away. So it's like, okay. Anyway, they get kind of confused. That's not what they expected, or maybe it is what they expected. Anyway, what they do in response is you actually, if you put a tiny microphone in your ear canal, you play one click in, you hear, echo is the wrong word, you'd have to have a very big head, but you hear clicks actually generated by your ear in decreasing amplitudes over time. It's because your ear is trying to amplify this original click, and the system doesn't work perfectly, at least not in our idea of an engineering sense, and you hear these clicks back at you. And in fact, Professor John Allen here is very famous for an invention he made in the 90s, which you can use on infants, right? You put a device in their ear, plays a click in there, and if you don't hear those echoes back, that means a really common kind of hearing loss for infants. And it's really useful to know when your infant has hearing loss because it's hard to tell otherwise. And for people that do know about it and do something about it, it's kind of curious because like those kids learn to talk a lot earlier, or learn language a lot earlier than other kids because you do you use your hands to communicate, right? And if you do that, if you use sign language, it just turns out kids can pick that up faster. So it's kind of a curious thing because in some ways they end up being really ahead. Obviously not being able to hear is not great in life, but they end up doing quite well if you can identify it. And if you can't, you just yell at them more and you wonder why they're kind of slow and never respond to things and don't learn stuff. So it's a very important invention he's got. And that was way back when he did that. Yeah. Those are autoacoustic emissions. What does that mean? Well, it's an active system. So if you can fool the system, you can actually make it make emissions when you're not putting in new sound. And you can hear that back again, right? If there's vibrations here, you can hear them back again through the three bones back into the eardrum. We good? Questions about that? How many people have had a class from Professor Allen? Cool. Are you grad students?
No.
Oh, okay. Did I describe this close to correct?
Our class is totally different.
Oh, your class was related. Oh, okay, good. It's always scary when students know that I'm BSing. But in any case, no, I think that's pretty close to correct. All right. Well, on the next page, there is stuff, there's homework stuff, and there's also stuff about the final project presentations. Please read that. The very first thing here it says is no PowerPoint. And I can always identify a student that never comes to class and never reads the handouts by coming in with a PowerPoint presentation. I'm not, PowerPoint, it's not fun enough. And you've got lots of experience doing that and other things. And really, it's not supposed to be an academic thing. You're supposed to show something cool you did in the Egan matrix and understand how you did it. So there's information about how you do it there, but you've only got about 5 minutes. It's not a formal presentation. I don't want you to worry overly much about it. I do want you to practice your presentation a little bit, make sure it actually works. I want you to make sure you have your stuff on the V drive, so if only one of the stations is in here, you can still do the presentation. But it's quite open. People generally enjoy it. Every time I've done a poll, people have said, yes, it's better to do two lectures where we just show presentations rather than hear you talk for 2 more lectures. So, hey, it's good with me. But I want you to take it seriously at the same time, not worried about it. It is not a concert performance. You're not going to be judged on how beautiful it sounds. Although, if you play an acoustic instrument and you want to process that sound, boy, that's an easy way to get something that's quite listenable, right? Just because if you play flute, say, and you process it, you can get some cool effects and take advantage of the fact that you know how to play flute. If you don't have your flute here, don't worry about it. It's a nerd fest where just people showing cool sounds. But the thing is, I'd like you to know, about the Egan matrix and show that you understand what your sound is doing, that kind of thing. Yes?
If we do use an instrument, do you have mics that we can use?
Yeah, there's mics in the lab. They're not great, but or do you mean real pickups? No, if you bring in pickup mics, actually. With all of this stuff, even if you use your voice, one trick I hear that doesn't happen so much in the lab is you got the speakers pointing at your microphone. Don't do that. Here we'll have speakers in here. Stand behind the speakers or something. That way you don't get the horrible feedback racket. But yeah, I don't have much. If you bring in your own pickups or pickups that you borrowed from somewhere, I don't want to know the details, then make sure you have phantom power turned off, right? Because when you use a microphone inputs with phantom power is keyword for roast whatever you put into it unless it's really a microphone. So be careful about that. Okay, thank you very much.